If I give you a box that splits one beam into two, and I let you rotate the box, your classical idea of spin will collapse in under a minute. Here's the setup. You've got a beam of particles, all identical, all moving in the same direction like a thin stream of dust in sunlight. They go into a device that has exactly two exits, an upper exit and a lower exit. If you place a detector at the upper exit, it clicks for some fraction of the particles. If you place a detector at the lower exit, it clicks for the rest. And the shocking part is that it's always the same two outcomes, not a blur, not a continuum. 2. Now, before we name anything, I want you to feel what kind of understanding we're going for. Not a definition you can repeat, not a formula you can copy. Understanding as in, if I rotate the box and I chain two boxes together, you can predict what happens without hand-waving. Ready for your first prediction? Most people think spin means an electron is a tiny spinning ball, and the magnet just finds which way it's spinning. Maybe it's spinning clockwise or counterclockwise. Maybe it's pointing up or down like a microscopic compass needle. That's the mental picture you're offered because your brain loves pictures. A spinning top is a picture. A compass is a picture. A little arrow is a picture. So let's see how far that picture gets us when we play with our two-exit box. Picture a beam of neutral atoms entering a magnet-shaped gadget and leaving as two perfectly separated beams. No smear, just two. The historical version of this is a Stern-Gerlach apparatus, a magnetic field that isn't uniform, so the force depends on how the atom's magnetic moment lines up with the gradient. But for now, don't get distracted by magnets and forces. Treat it as a black box with two lanes. I'll label the box by the direction it's asking about. If the box is oriented along what? We'll call the Z direction. I'll call it a Z box. It's an analyzer. It takes an incoming beam and sorts it into two beams. One beam I'll label Z plus and the other Z minus. That's just a name for upper and lower. It's not yet a claim about what's inside the particle. Now here's something you can do immediately. You can block one exit. Put a little absorber in the Z minus path so only the Z plus path continues. Then what you have downstream is a beam that is definitely Z plus in the only sense that matters operationally. If you send it into another Z box oriented the same way, it always comes out the Z plus exit, every time. That's already a big step. We've defined a state without metaphysics. A state is simply a preparation procedure that makes a stable prediction about the outcomes of some measurement. Z plus is what you call the beam that passes the Z plus filter. So far, nothing feels mystical. It's like sorting marbles by size. But now I'm going to rotate the question. Suppose I take your beautifully prepared Z plus beam, filtered, clean, no Z minus left, and I feed it into a second box, but this time the box is oriented along a different direction, X. Same kind of box, same two exits. One exit I'll call X plus, the other X minus. Keep X plus. Now measure along an axis halfway between X and Z. Call it N. Keep N plus. Now measure along Z again. If you treat the state as a point on the sphere that gets snapped to the axis you measure, each selection moves your point. Z plus snaps you to the North Pole. X plus snaps you to the equator point. N plus snaps you to an intermediate point. Each snap changes the probabilities for the next measurement. The sphere picture makes your intuition match the results. But here's the punchline. There is no way to assign a single pre-existing set of plus-minus answers to all possible axes such that the statistics of these sequences come out right. The act of choosing which axis to measure is not selecting from a pre-written answer key. It is participating in the definition of the outcome set for that trial. Again, that's not philosophy. That's the content of what the chained Stern-Gerlach-style experiments tell you. Now you might wonder, why is it always two outcomes? Why not three or a smear? Some particles do have three outcomes in analogous setups. That corresponds to spin-1 systems, where measuring a component yields short 1, 0, or plus 1 in units of h. So two outcomes is not a universal rule of nature. It's a property of certain systems. The reason we focus on spin-1/2 is that it's the simplest non-trivial case, and it's the one electrons have. So our box is not a universal quantum box. It's a very specific kind of object, a two-outcome analyzer for a spin-a-half degree of freedom. And the amazing thing is, once you accept the rule book of this box, you can explain a lot of chemistry, magnetism, and the stability of matter, not because spin is an extra decoration, but because it changes the counting of states in profound ways. Let's touch that payoff carefully, because it's easy to rush here and lose the conceptual thread. Electrons are fermions. They have spin 1/2, and fermions obey the Pauli exclusion principle. You cannot put two identical fermions in the same quantum state. In atoms, that means you cannot pile all electrons into the lowest energy orbital. They have to occupy different states. Spin doubles the capacity of each spatial orbital because an electron can be in the same spatial wave function with spin up or spin down relative to some axis. That doubling is one reason the periodic table has the structure it has. But notice what makes that statement meaningful. Spin up or spin down is not a little arrow physically pointing. It's a label for two orthogonal states of a two-state system. The exclusion principle is about states, not about arrows. If spin were literally a classical rotation, you might imagine electrons in an atom as tiny spinning tops jostling around. That picture would not naturally lead you to the rigid structure of electron shells. The state-based picture does. So understanding spin as a two-state quantum degree of freedom is not just an intellectual tidbit. It is part of the reason solid matter is stiff, why chemistry has rules, why magnets can exist, why your chair is not a fog. Now let's return to the emotional core of the title. No one can make you understand spin like this. The promise is not just that I'll explain it differently, but that at the end you'll feel that spin could not have been anything else given the experiments. Let's synthesize the whole story in one continuous line. We start with an apparatus that asks a yes-no question about a system along a chosen direction and routes the system into one of two output channels. When we filter, we prepare a state that gives certainty for that same question. When we ask a different question, certainty becomes probability. When we ask the original question again, the original certainty is not automatically restored, because the intermediate measurement did not merely reveal, it re-prepared the state. The dependence of probabilities on angle is smooth and geometric, and the full transformation properties under rotation reveal that the underlying state is a spinner. It can acquire a minus sign under a 360-degree rotation, a sign that becomes physically meaningful only in interference experiments where relative phase matters. That is spin. Spin isn't a thing spinning. It's the rule book for how a quantum two-state behaves when you rotate the question you ask. And once you accept that, a lot of phrases people toss around become clear instead of mystifying. Spin along Z becomes a state that yields Z plus with certainty if measured along Z. Measuring along X changes the spin, becomes the X measurement produces an X eigenstate, which has uncertain outcomes for Z. Non-commuting observables becomes the order of asking questions matters because each question changes the state in a specific way. 120-degree symmetry becomes quantum states transform under rotations with a hidden layer that can flip sign revealed through interference. Now there's one last thing I want to do for you. Ow, because it's where many people either finally relax or get tense again. You might be thinking, okay, but why does nature use complex numbers and phases and all this SU2 stuff? Why can't there be a simpler underlying story? And here is the Feynman-style honest answer. We don't know a deeper why in the sense of a mechanical model like gears turning behind the scenes. We know the why in the sense of these are the simplest rules that fit the experiments and preserve the symmetries we see. The mathematics is not decoration. It is the compressed description of the constraint set. If you insist on a deeper classical mechanism, you can try. People have tried for a century. The more you demand classical pictures, the more you end up inventing hidden structures that behave exactly like the quantum state anyway, just disguised. So there's a kind of peace that comes with understanding spin properly. You stop demanding the wrong kind of explanation. You stop asking, what is it really doing like a little machine in it? And you start asking, what are the operational rules and how do they connect to symmetry and probability? And when you do that, the weirdness becomes coherent It becomes a different kind of normal. Here's a final way to test whether you truly have it. If I tell you I have a beam prepared in Z plus and I rotate my analyzer by 90 degrees to measure X, you can predict that I'll get a split, roughly half X plus and half X minus. If I then take only X plus and measure Z again, you can predict a split again. And if I rotate my analyzer by a small angle instead of 90 degrees, you can predict that the certainty will degrade smoothly, not collapse randomly. And if I build an interference experiment sensitive to phase, you can accept, without feeling cheated, that a 360-degree rotation can matter through a sign flip. That's understanding. It's not a picture of a spinning ball. It's a mental simulator for what the world will do. Once you see spin this way, magnets, chemistry, and even quantum computing stop being separate topics. They become different ways of exploiting the same two-state logic. A qubit in quantum computing is, at heart, a spin-on half-like system. Two outcomes under measurement, a continuum of possible preparations, and phases that matter when you do interference between alternatives. The reason you can do anything interesting with qubits is the same reason our chained boxes behave the way they do. The state is richer than a classical bit, even though measurement gives only two answers. So the next time you hear someone say, the electron is spinning, you can translate it in your head into the honest version. The electron has an intrinsic two-state degree of freedom that transforms under rotations as a spinor. And if that translation feels heavy, you can translate it again into the version you can actually use. There are different questions I can ask, each with plus-minus answers, and the rules of those questions don't fit a hidden arrow in 3D space. And that's a strange kind of gift, the universe telling you that direction is not always what you think it is. If you want to keep going after this video, don't chase more vocabulary, chase more experiments. Take this same box logic and apply it to polarization of light, to interferometers, to entanglement, to Bell tests. Each one is the same lesson in a new costume. Your classical pictures are not wrong because you're not clever enough. They're wrong because the world is constrained in a different way than classical pictures assume. So here's an open question to leave you with. Not a mystery for mysticism's sake, but a practical curiosity. If the state is the predictor for outcomes, and if rotations act on that state in this spinor way, what does space itself mean at the quantum level? Is space the stage, or is space partly defined by the kinds of transformations states can undergo? When you rotate a measuring device, you're rotating a physical object in space, yet the thing that responds is a quantum state that lives in a different kind of space, the space of possibilities. That overlap between physical rotation and abstract transformation is where modern physics keeps finding its deepest structure. And now when someone says spin is confusing, you can smile a little because you know exactly where the confusion comes from. It comes from trying to make the universe use the wrong kind of picture. Here's the prediction trap. If the particle carries a hidden little arrow in space, and the first box merely revealed the arrow was up along Z, then what should happen when you measure along X? You might say, well, if it's really pointing up along Z, then along X it should sometimes look like plus and sometimes minus depending on the angle between Z and X. Fine, you expect a split, and that expectation is actually compatible with what happens. If you take Z plus into an X box, you get two outputs. Typically half go to X plus and half go to X minus if the axes are at 90 degrees. Okay? Still no disaster. But now we do the move that makes spin stop being a picture and start being logic. Take the X box outputs and immediately feed them into a third box oriented along Z again. So the chain is Z box, filter to Z plus, X box, Z box. Before I tell you what happens, lock in your classical intuition. If the particle had a definite spin direction that the first Z measurement merely discovered, then after the detour through X, what should the final Z measurement show? You'd probably say, it should still be Z plus all the way, because we started with Z plus. We filtered out Z minus. We didn't do anything physically violent like knock the particle around randomly, at least not in the mental model. We just looked at it in a different way. If measurement is just revealing, then looking along X shouldn't destroy the fact that it was Z plus. So you predict final Z box gives only Z plus. Nature's response, wrong. What you actually get is that the final Z measurement is no longer certain. After the x box, if you measure z again, you get a split. Some come out z plus and some come out z minus. And if the x measurement was at 90 degrees, it's typically about half and half. That single result is the guillotine for the hidden arrow revealed by measurement picture. Because if the RSZ filter produced particles that truly carried Z plusness as a permanent property, then inserting an intermediate measurement along X should not bring Z minus back from the dead. You killed the Z minus beam upstream. Where did it come from? At this moment, a lot of people try to patch the classical picture by saying, but measurement disturbs the system. That's true as a statement, but it's not understanding yet. The question is, what kind of disturbance is so specific that it doesn't just add noise, but produces exactly the patterns we see when we rotate and chain these boxes? Let's stop calling it disturbance like it's a vague shake. Let's describe what the X-box actually does operationally. The X-box takes whatever beam you give it and outputs either X plus or X minus. If you block one of those exits, you can prepare a beam that is definitely X plus. And if you send that into another X box, it stays X plus with certainty. So the X plus beam is as real and as stable as Z plus, just defined relative to a different orientation. Now watch what that implies. If you start with Z plus and you pass through an X box, and then you select only the X plus output, meaning you physically block X minus, then you have prepared an X plus beam. Downstream, it's X plus with certainty. But if you then measure Z, you get a 50-50 split. So the intermediate box didn't merely read some pre-existing X value, it re-prepared the state. It took your Z plus preparation and turned it into an X plus or X minus preparation depending on which path you keep. That's not a philosophical statement, it's a practical one. The state after the box is determined by which exit you chose to keep. At this point, you can summarize the logic in a way that doesn't mention electrons spinning or magnets tugging. It's a rule book for a two-outcome system. 1. There are different questions you can ask, Z, X, and any direction in between. 2. Each question has two possible answers, plus or minus. 3. If you filter for a definite answer to one question, then asking a different question produces uncertainty. Asking that different question doesn't just reveal information, it changes what future questions will answer with certainty. Now I'm going to make this feel less like an abstract rulebook and more like something you can hold in your hands. Think of the particle not as a spinning object, but as a passport going through checkpoints. You go through a Z checkpoint. The guard stamps your passport, either Z plus or Z. If you only allow people with a Z plus stamp to continue, you now have a crowd that is guaranteed to pass a second Z checkpoint with a Z plus stamp again. That's what Z plus state means. But here's the non-classical twist. The X checkpoint doesn't look for a hidden X stamp that was already on the passport. It issues a new stamp based on the rules of that checkpoint. And once it stamps X plus, it doesn't leave the old Z stamp as the meaningful predictor for what happens next. Downstream, the passport behaves like an X plus passport for predicting X checkpoints, and its Z behavior becomes probabilistic again. In the real physics we have on, I'd saying the stamps are literally written in ink. The stamp is the state. The state is the complete predictor for what happens at later checkpoints of various orientations. Does that mean the particle has no properties at all? No, that's too extreme. It has stable properties like mass and charge and spin magnitude. But spin along Z is not a property the particle carries around like a tattoo. It's a relationship between a state and a measurement orientation. So what is spin then, if it's not a tiny rotating ball? Let's approach that question the Feynman way. Not by describing what spin really is in the metaphysical sense, but by describing the simplest mathematical object that behaves exactly like the boxes behave. We need something that can be prepared in two distinguishable ways relative to any axis, and that changes in a precise way when you rotate the axis. And we need it to explain why Z and X are incompatible, why knowing one with certainty implies uncertainty in the other. Here's the sentence that sounds abstract, but is actually the cleanest anchor you can get. Spin and a half is the simplest quantum system. It's the simplest possible kind of two-state that still remembers continuous directions. That last part matters. Two-state sounds like a coin, heads or tails. But a coin does not have an infinite family of different questions you can ask it. A coin has one main question: is it heads or tails? You can flip it, but you're not rotating a measurement basis in a continuous way that changes probabilities smoothly. Spin 1/2 is a two-outcome system with a continuum of measurement directions, and that combination is so restrictive that the geometry of the state space becomes almost forced. Let me show you why without writing a single matrix. Suppose you have a Z-box and you rotate it slowly toward the X orientation. What happens to the outputs? If this were a classical arrow that you're projecting onto an axis, you might expect the outcomes to change gradually. And in fact, they do change gradually. If you prepare Z plus and then measure along a direction tilted by a small angle, you don't suddenly jump from certainty to 50-50. The probabilities slide smoothly. That smooth sliding is a huge clue. It tells you that the state isn't just plus or minus. The state must encode something like an orientation, because rotating the measurement changes outcomes continuously. Yet whenever you actually measure, you only ever see plus or minus. 2 clicks, 2 spots, 2 exits. So you have a system that stores something continuous, but reveals itself in discrete answers. Now, there are many ways to imagine continuous hidden variables. But our chaining experiment already killed the naive version where the hidden continuous thing is a classical arrow in 3D space that measurements merely reveal. So if the continuity is there, it's not a classical arrow. It's something else. Here's a way to feel what that something else must be. Take a Z plus beam. Measure along an axis tilted by 45 degrees between Z and X. Call that direction N. Feed Z plus into an N box. You get N plus and N minus with some probability. Now take the N plus output and measure along Z again. You'll get Z plus more often than Z minus because N is closer to Z than to X. That makes sense qualitatively. But the key is, the probabilities depend on the angle in a very specific way. The dependence is not linear in the angle. It follows a squared cosine type law for spin-1/2. You don't need the exact formula to understand the structure, but you do need to understand that the state behaves like a unit vector on a sphere of possible preparations, and measurement outcomes relate to angles between these preparation directions and measurement axes. So when people talk about the block sphere, they're not introducing a fancy picture for fun. They're saying, if you want a two-state quantum system that changes smoothly under rotations and reproduces the chaining behavior, the set of pure states can be represented as points on a sphere. And that sphere is not the physical space the particle moves in. It's a sphere of states, a map of preparation possibilities. Let's make that concrete. If the system is prepared in the Z plus state, put a dot at the north pole. Z minus is the south pole. X plus and X minus are points on the equator at opposite ends. Any intermediate preparation corresponds to another point on that sphere. Now suppose you measure along Z. What does that mean in this picture? It means you are asking, is the state aligned with north or south relative to the Z axis? And the probability of getting Z plus depends on how close the state point is to the north pole. That makes it sound like we've smuggled the classical arrow back in. But notice the difference. The arrow is not a physical arrow in real space. It's a representation of the state in an abstract space that's designed to predict measurement outcomes. It's a compact summary of how the system responds to any orientation of your box. So when I say spin points along X, I'm not claiming there's a tiny arrow physically pointing along X. I'm saying the state is such that if you ask the X question, you get X plus with certainty. That's a promise about outcomes, not a picture of a rotating object. Now you might ask, why call it angular momentum at all? Why call it spin? Because it behaves like angular momentum in some important ways. It couples to magnetic fields like a magnetic moment. It has quantized components. It adds in specific ways when you combine particles, and it fits into the deep symmetry structure of rotations. But you can appreciate that without believing the particle is literally rotating like a ball. In fact, trying to imagine a literal spinning electron leads you into trouble fast. If the electron were a tiny charged sphere spinning fast enough to produce the observed magnetic moment, parts of it would have to move faster than light. That's your clue that the classical rotation picture is not merely incomplete, it's the wrong category. So if spin is not a spinning object, what is it? Here's the honest answer. Spin is an intrinsic quantum degree of freedom that transforms under rotations according to a particular mathematical rule. And the simplest non-trivial rule is the spin-em-half rule. That's the what. Now let's make the how feel inevitable, because the title promised understanding, not vocabulary. Go back to the boxes. The boxes respond to rotations in a way that suggests something deeper about rotation itself. In ordinary life, if you rotate an arrow by 360 degrees, it comes back to itself. Turn a compass needle around in a full circle, and it's the same needle pointing the same way as before. Rotate a book 360 degrees, and it's back where it started. So you'd expect that if you rotate your entire apparatus by 360 degrees, nothing physically changes. And in many experiments, nothing measurable changes. If you only look at probabilities at a single analyzer, a full 360-degree rotation doesn't change the probabilities, so it would be natural to think 360 degrees is truly nothing. But here comes the part that sounds like a prank. Rotate a spin-a-half system by 360 degrees and it doesn't truly come back. It comes back with a hidden minus sign. What does that even mean? A minus sign compared to what? If all you ever see is plus or minus outcomes at an analyzer, how could a global minus sign matter? Great question. The answer is, it matters only when you have a way to compare phases, meaning when you have interference between two paths. A global phase on a single isolated state is unobservable, but a relative phase between two components that later recombine can show up as different detector clicks. So to see the minus sign, you need an experiment that is more like a maze with two roots that rejoin, not just a fork that ends in detectors. Here's a mental version of such a maze, still using our box language. Imagine your analyzer doesn't immediately destroy the particle when it exits. Instead, it coherently splits the beam into two paths, like a fork in a waveguide, and you can later recombine the paths in a way that allows them to interfere. This is not science fiction. This is how interferometers work for photons, and there are analogous setups for particles with spin, where you can create and recombine superpositions. Now, suppose you prepare a state that is a coherent superposition of Z plus and Z minus, meaning it's not that the particle secretly chose one path, rather the state includes both possibilities with some relative phase. If you now perform a 360-degree rotation operation on the spin state, the spinor mathematics says the state vector picks up a factor of 1. That doesn't change probabilities by itself because probabilities involve the magnitude squared. But if only one arm of your interferometer undergoes that rotation, then the relative phase between the two arms changes by p, which flips interference fringes. Peaks become troughs. Detectors that used to click now go quiet, and vice versa. That's the physical meaning of the minus sign. It's not mystical. It's a statement about how the state transforms under rotations, and how that transformation becomes observable when you compare two histories. Now, why on earth would nature choose such a rule? Because the analogies of diptous, lying symmetry group of rotations for quantum states is not the same as the group of rotations for classical arrows. Classical orientation in 3D space is described by rotations that form a group called SO3, but the quantum state of a spin 1/2 system transforms under SU2, which is like a double cover of SO3. In plain language, there are two distinct quantum states that correspond to the same classical orientation, differing by a sign. A 360-degree rotation takes you from one to the other. Only after 720 degrees do you return to the exact same quantum state. If that feels too abstract, good. It should feel abstract until you connect it to something your hands can do. There's a classic physical demonstration sometimes called the belt trick or the plate trick. You hold your arm out with a plate in your hand, rotate the plate 360 degrees, and then, without rotating the plate back, you can move your arm and the belt around in a way that untwists the belt, but it takes a full 720-degree process to return everything neatly. The point of that demo isn't that your arm is an electron. It's that the space of rotations has a subtle topology. There's a notion of rotation history that isn't captured by just the final orientation of an arrow. Two configurations that look identical in terms of a visible arrow can be connected or not connected without cutting through a twist. Spinors behave like they remember that kind of twist. They're sensitive to the path through rotation space, not just the final direction. Let's connect this back to our original promise, making you understand spin. Understanding spin means you stop asking, which way is it spinning, and start asking, what are the rules for how this two-state responds when I rotate the measurement question, and how do sequential questions interact? Now, I want to give you another prediction trap, because prediction is where understanding shows itself. Suppose you have Z plus prepared. You send it into an X box. You get two outputs, X plus and X minus. Now you block X minus and keep only X plus. So now you have an X plus beam. If you now send that X plus beam into a Z box, you get a 50-50 split. So far, so good. But here's the question. What if instead of measuring X in the middle, you measure along an axis that is just barely tilted from Z, like 1 degree off? What do you expect the final Z's certainty to do as you make that tilt smaller and smaller? If measurement were a violent disturbance that scrambles the state randomly, even a tiny tilt might destroy the Z certainty. But that's not what happens. The loss of certainty is gentle. The probability of returning Z plus remains very close to 1 for a tiny tilt and only becomes 50-50 when you tilt to 90 degrees. That tells you the state change caused by measurement is not random noise. It has structure. It depends smoothly on the orientation of the measurement. The system is exquisitely sensitive, but in a controlled, geometric way. And that geometric dependence is exactly what the block sphere captures. The sphere is the map that turns angle between preparation and measurement into probabilities. Now, we can make a clean conceptual leap that many explanations skip. In quantum mechanics, the measurement axis isn't just a way of peeking at a pre-existing arrow. It is a way of defining what you even mean by plus and minus. Different axes define different decompositions of the state. So asking what is the spin along X is not like asking what is the temperature, where the system has a definite value whether you measure it or not. It's more like asking, when I put on this particular pair of glasses, which of these two labels will the world let me attach to the state? That's why spin is often the first place where people truly feel the non-classical nature of quantum states. It's the simplest arena where incompatible questions exist and where the order of asking questions matters. Let's talk about order because this is where understanding turns into power. Consider these two sequences. Sequence A, measure Z, then measure X. Sequence B, measure X, then measure Z. Do you get the same statistics? Not necessarily, because the first measurement prepares the state that the second measurement acts on. So the order matters. In classical physics, if you measure the x-coordinate of a particle and then the y-coordinate, you can imagine you're just revealing two independent facts about where it is. Order doesn't fundamentally matter if your measurements are gentle and your model is deterministic. In spin, order matters because the measurements correspond to different ways of carving up the state space. They are non-commuting operations in the mathematical language, but you can feel it without that word. Once you choose X and filter for X plus, you have created a state for which Z is uncertain. If you choose Z and filter for Z plus, you have created a state for which X is uncertain. This is not a weird add-on. It is the core of what spin is. Now let's address a question that naturally follows. If the state isn't a hidden arrow, what is it physically? Is it just information? Is it just our knowledge? Careful, the state behaves like information in that it summarizes predictions and it updates when you measure. But it's not merely subjective knowledge, because you can prepare states reproducibly, and two observers can agree on statistical outcomes without talking to each other as long as they know the preparation procedure. So the state is an objective feature of the preparation and measurement setup. It is the best compact description of what will happen in repeated trials. It's not in your head, but it's also not a classical attribute like a tiny arrow glued to the particle. That in-between status is exactly what makes people uncomfortable, and exactly why spin is such a perfect teaching tool. Now let's revisit the name spin and decide what we're allowed to say honestly without lying. We are allowed to say spin is a kind of angular momentum, not because something is literally spinning, but because it participates in the conservation and symmetry laws associated with rotations. If you Rotate your apparatus, the physics transforms in a specific way, and spin is the label for how the quantum state transforms. We are allowed to say, spin couples to magnetic fields, producing measurable effects like splitting beams in Stern-Gerlach. We are not allowed to say an electron is a tiny charged sphere physically rotating, because that picture doesn't just simplify, it contradicts reality. So what picture can we keep? Here's a picture that is honest. Spin is like an internal two-state orientation that is not an orientation in ordinary space, but is related to space through how it responds to rotations and magnetic fields. It's like the particle carries a tiny two-dimensional compass that does not live on the same map as your three-dimensional compass. Yet whenever you choose a direction to ask about, it answers plus or minus, and the statistics depend on the angle between your chosen directions. If that sentence felt slippery, let's tighten it with a direct, testable claim. When you prepare a spin 1/2 system in Z+, and you measure along an axis tilted by angle θ from Z, the probability of getting plus along that axis depends only on θ in a smooth way that matches the geometry of the state sphere. That's what the state is, a point on that sphere that rotates when you rotate the system. Now, there's a subtlety here that matters for deep understanding. Rotating the measurement apparatus is not always the same as rotating the state. Sometimes you rotate the magnet, sometimes you rotate the source, sometimes you rotate both. But the key symmetry idea is only relative orientation matters. The theory must be consistent under rotations. And that consistency is precisely what forces the spinor behavior. Because the state space is not just a sphere, it has an extra layer of phase that the sphere picture hides. Two opposite points correspond to orthogonal states, yes, but the full state has more structure than a point on a sphere. That extra structure is exactly where the 720-degree sign flip lives. If you want the cleanest intuition, the block sphere tells you everything about measurement probabilities for a two-state system, but it does not show you the global phase. The phase usually doesn't matter until you build interference experiments. Then phase becomes physical. So how do we talk about phase in a way that doesn't turn into mystical poetry? Phase is a number that tells you how two parts of a superposition will add when you recombine them. It's like timing in two wave trains. If two waves are in step, they reinforce. If they are out of step by half a cycle, they cancel. That's all phase is, a relative timing in the wave-like structure of the quantum state. It's not a hidden rotation in physical space, and it's not a secret variable that determines outcomes. It's the ingredient that makes interference patterns possible. Now connect that to rotations. Rotating a spin-a-half system changes its phase in a way that is not visible in single outcome measurements, but is visible in interference. That is why the 360-degree minus sign is both true and in many everyday content. Exts, invisible. The world doesn't show you phase unless you ask the kind of question that can see it. Now, if you've been holding on to one last classical hope, it might be this. Okay, maybe the particle does have a definite spin direction, but measuring along x randomly flips it sometimes, and that's why z is uncertain afterward. That sounds plausible until you try to build a consistent model for all angles and all sequences. The pattern of probabilities is too clean, too geometric, too dependent on angle in a specific way. Random flipping doesn't reproduce it. You'd need a disturbance rule that depends on the measurement axis, depends on previous measurements, and reproduces interference effects. At that point, you have essentially reinvented quantum state update, just with extra words. Quantum mechanics is not weird because it is unpredictable. Classical systems can be unpredictable too. Quantum mechanics is weird because it is constrained. The constraints are symmetry and the structure of probability. Spin is where you first feel those constraints clamp down. You don't get to imagine whatever hidden mechanism you like. The experiments box you in. Let's do one more experiment in your head to make the constraint feel absolute. Start with Z+, measure along X.